do supervised domain adaptation. It's kind of strange. I mean, my feeling is that things actually change a lot once someone starts handing you target labeled data. And there's actually been very little work trying to combine the stuff that I talked about in the first part with the stuff that I'm going to talk about now. And I think that that's partially because it's like, maybe I'll come back to it at the end. So there are two, I think, styles of supervised domain adaptation. So one style is I have lots of labeled data, say from Wall Street Journal, and I want to do well on emails. And so someone gives me a little bit of labeled data on emails. And so now my job is to build a model or a classifier that does well on emails, getting most of its strength from the huge amount of labeled data that I have from Wall Street Journal, and then using the small amount of labeled data from emails to like tweak or change things around so that it's better for emails than for Wall Street Journal. So that's kind of the first setting. And then the second setting is maybe I have more than two domains. So in the reviews data, we have like books and movies and music and videos and kitchen appliances and cars and cell phones and cameras and whatever, right? So each of these things you can think of as a different domain. There are going to be some things that are common to all of these, right? So like if I say that something is good, this is probably positive, irrespective of what the product actually is. But if I say something is exciting, and maybe this is good for a book, maybe it's not good for, I don't know, a blender or something like that. So anyway, I'll talk about both of these. I mean, I think, like personally, the first style is where I think most of the work early on in this area happened, and I think things are shifting to the second style. But I think that that's kind of because we can do a really good job at the first one, and there's not that much more interesting to do. So there are two basic approaches. So there's I sort of categorize them as feature-based algorithms and parameter-based algorithms. They're very close because features and parameters are very close, but I think they give sort of two different ways of thinking about the problem. And so we'll start off with feature-based stuff and then move on to parameter-based stuff. Okay, so here's an example from the review. So in books, saying that a book is thrilling is probably good. Saying that it's horrible is probably bad. In restaurant, horrible is still probably bad. Thrilling, I don't know. Maybe there's a better, if anyone can actually come up with a better example than thrilling, this was the best I could come up with, I'd be happy to hear your example later. Do you have an example?
Well, you could use a different word like hot, and if you're talking about ice cream, then it's bad. If you're talking about...
That's true. So actually, this came up recently. Yeah, so I guess this is sort of an issue of like, where do you define the boundary between domains, right? So, there's going to be, if we're talking about sushi, like fresh is always going to be positive. But like if we're talking about restaurants, like is romantic positive or not? I don't know. I mean, like maybe I like romantic restaurants, but you don't like romantic restaurants or something. So anyway, so maybe the example's not the best. But there are some things like horrible that we want to share across the domains. They're going to behave consistently regardless of whether we're talking about a book or whether we're talking about a restaurant. And then there are some features, in this case like thrilling, that we don't want to share, that we want to learn, this is how thrilling behaves for books, and this is how thrilling behaves for restaurants. And we don't want there to be too much of a relationship between these two. So one thing I could do is I could say, okay, here's my vocabulary of 50,000 words. I'm going to go through each word, and I'm going to say, okay, I want to share this word, I don't want to share this word. I want to share this word, I don't want to share this word. But I don't want to do that because it sounds really painful, and I probably won't do a very good job anyway. So what we're going to do is we're just going to sort of feed this into some off-the-shelf learning algorithm and let the algorithm decide which is which. Okay, so this is the basic idea behind a set of techniques which I'm sort of all lumping under the idea of feature augmentation. So here we have two examples. We have the book is thrilling, the restaurant is thrilling. So if I do some like bag of words extraction, then my example for this guy might have four features. A feature saying the word the occurs, a feature saying the word book occurs, a feature saying the word is occurs, and a feature saying the word thrilling occurs. I could have more, but let's just say these are my four. Then I'm going to do the same thing on the restaurant side, so I get four features. Three of them are the same, and then instead of having the book feature, I have the restaurant feature. Okay, so I can use these features and I can learn some model. But if I learn a model based on these features, then it's forcing the model to essentially agree between the domains as to whether thrilling is a good feature or a bad feature. Okay, so I want to allow the model to have the opportunity to say, well, in one domain, thrilling is good, and in the other domain, thrilling is bad. So I'm going to do this by just adding a bunch of extra features. So for every source example, I'm going to duplicate all the features, but instead of calling them like word thrilling and word is, I'm going to call them source thrilling and source is. Okay, and then I'm going to do the same thing over on the target side, where instead of word is word thrilling, I'm going to have target is target thrilling. Okay, so these top guys are my original features. For source examples, I duplicate them and call them something slightly different. And then for target examples, I duplicate them and call them something yet again slightly different. Okay, so the idea is if I want to learn something that's common to both domains, I can use these the original features. So if I have an original feature for good, I can assign a high weight that says if you contain the word good, no matter what domain you're in, you should be labeled positive. And if I want to assign, if I want to make distinctions that are domain specific, then I can say, okay, for this source word thrilling, I'm going to give you a high positive weight because you're indicative of a positive example. And for the target word thrilling, I'm going to give you a high negative weight, saying that you're really indicative of a negative example. Okay, so it basically gives whatever learning algorithm I feed these features into the opportunity to make its own decisions about what's shared and what's not shared. So if you like sort of feature vector representation, so I get my document and I map it through some function phi into a vector. So this phi is what's mapping this document into this original feature vector. So what I'm doing on the source domain is I'm saying, okay, take all of my original features, then make another copy of them, and then stick a bunch of zeros. So this is like the original features, the copy of them, and then a bunch of zeros. And then for target examples, take the original features, and then a bunch of zeros, and then the original features again. All right, so however you want to think about it is fine. So for those of you who like kernels or know about kernels or whatever, you can think about this in a kernel sense too. So if we take these feature vectors and we assume that they correspond to some kernel k, so if k is the kernel in the original space, then to get to the kernel in this expanded space, you basically just double the value when your two examples come from the same domain. Okay, and it's basically because if you take a dot product between a source example and another source example, you're going to get double credit for these two. But if you take the dot product between a source example and a target example, then you'll only get credit for this first component, and these second two will go to 0. So I should say this 2 is arbitrary. You could replace it with any constant. Doesn't really matter. Okay, so I think one thing that's interesting to notice here, or two things that are interesting to notice, is that we're ensuring that single good hypothesis holds. So single good hypothesis says there's a single classifier that works well on both domains simultaneously. And by doing this feature augmentation, we've basically created a situation where even if the source domain and the target domain have absolutely nothing in common, I can still learn a single classifier that does well. It'll just ignore this first part, and then whatever's the best thing to do on the source domain, it'll do on the second component, and whatever's a good thing to do on the target domain, it'll do on the third component. Okay, so by doing this expansion of features, we know that single good hypothesis is going to hold. And then we've also completely destroyed shared support. So there is no longer any shared support here, because all source examples always have zeros in these last components and non-zeros in these second to last components, and then vice versa for target examples. So, on a third of our dimensions, we never see anything from source, and on another third of our dimensions, we never see anything from target. So there's no way they have shared support. I'll come back to that in a second. Okay, so if you run this on some data, you actually get some sort of interesting effects. So what we're looking at here is the weights for a single feature for different classes and for different domains. So here we're doing named entity recognition. We're trying to predict whether words are people, geopolitical entities, which are things like countries and stuff like that, organizations or locations. And then we have our general feature, which is the shared feature across all the domains. And then we have broadcast news features, conversation features, newswire features, weblog features, Usenet features, and telephone features. And basically, white indicates positive weight, black indicates negative weight, and the bigger the box, the larger magnitude. Okay, so this is a really big positive weight, this is a pretty big negative weight. So this feature is the feature Bush. And what we see is that in general, Bush is a person, which is fairly reasonable. Sometimes it's a geopolitical entity, so this would be in cases of metonymy. So if you say Bush declared war on blah, 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 it's not really Bush declaring war, it's America that's declaring war. So Bush is standing in for a geopolitical entity. Bush is almost never an organization, and it's sometimes a location. And this, I actually looked, this is the case where you're talking about standing next to a bush or something like that. And essentially, what happens is in broadcast news, Bush is almost never anything except a person. So the broadcast news features get way higher weight for person and then negative weight for geopolitical entity and organization. And so this bigger black basically completely demolishes this small white. So it's basically saying in broadcast news, never label Bush as a geopolitical entity. On the other hand, in Usenet, so in news groups, Bush is almost always a geopolitical entity. I mean, okay, so he's also a person, but he's used much more commonly as a geopolitical entity than anywhere else. Okay, so it seems to be doing something kind of reasonable. And then I looked at something else, and this really confused me. So this is the weights for when the previous word is the. Okay, so I have a sentence, blah, 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 the something, and I'm trying to label something. Okay, so what we see is that when you're preceded by the word the, in general, you're never a person, you're never a geopolitical entity, you're never an organization, you're never a location. Except in conversations. And in conversations, you get these giant positive weights that overwhelm the general weights that say if you're preceded by the word the, actually you are often a person, GPE, organization, and location. Anyone know why this happens? They do say the a lot, but why is it followed by entities and conversations and not elsewhere? So I couldn't guess. I had to look it up. I went into the data. It turns out that that people in conversations say things like the Iraqi people or the Pentagon or the cabinet or the government or these sorts of things. But you almost never see this in any of the other domains. So basically what it's figured out is that in conversational speech, the is a good indicator of a named entity coming next, whereas in basically every other domain, it's a really bad indicator. And I think this is a really good example of a case where a machine learning algorithm is doing something that's actually smart and actually makes sense based on the data. But if you had asked me to go through the features and say what's indicative of being a name, having the previous word be the, I would have expected no difference between domains. So I think this is kind of a nice success case of the algorithm doing something reasonable.
I'm wondering how this is different from just training a bunch of classifiers on all the different things individually and not doing this
Okay, so I will answer that question on the next slide. So it works better. So if you train them completely before I do that, well, I'll put it up. You can be scared by the giant table. But I mean, basically, if you're training them completely separately, then you're not allowing one domain to help the other domain in any way, right? And so what we're hoping is that by training them together, we can allow them to help each other and not hurt each other. So this is what we're looking at. So we have 6 tasks. So this is the named entity recognition task. Here are the different domains. So broadcast news, broadcast conversations, newswire, weblogs, Usenet, conversational telephone speech. And then this is also named entity recognition data. This is part of speech tagging. This is like recapitalization. This is chunking, blah, blah, blah. It doesn't really matter. But we have a lot of data sets. And what we have here is this is your error rate if you train. OK, so here we're trying to predict on broadcast news. So this is if we train on everything other than broadcast news. And this is if we train only on broadcast news. Okay? And then you can ignore these 2 columns for a second. And then this is what we get if we do this feature augmentation thing. So training completely separately is kind of like doing this target only. And so basically what we see is, so bold means we win. Not bold means we don't win. Sometimes we tie. But overall, we win on most stuff. Sometimes we tie, sometimes we don't. You might ask, okay, so we won on all of this stuff. We won down here. We lose here. So why are we losing here? And at the time that we were doing this, we had a hypothesis. So the hypothesis was that if we look at the cases where we win, it's precisely the cases where you can do better training only on the target domain than you can training only on the source domain. Okay, so I give you source data, I give you target data, you train a model on exactly one of these. One of them is going to do better on target data. Okay, in general, we're going to have much more source data. Okay, so the only way that the target model can beat the source model is if the domains are reasonably different. If the domains are very similar, since we have so much more source data, the source model should just win because it has more data. So it's only going to be the case when the domains are reasonably different that the target model does better than the source model. And it turns out that exactly those cases where the target model does better than the source model are the cases where the augmentation is doing better than anything else. Okay, so this was kind of it was an observation. There wasn't really any justification for it. I think my sort of hand-wavy justification is, well, if you're doing better using the source data alone than using the target data alone, then do you really expect the target data to help you that much? I mean, you're already doing so well just with the source data. But we actually have a better explanation now. So you can prove something, and this is actually way, way nastier. It takes like 2 lines to write it out in a paper. But I've just put big O of stuff to hide the stuff that I don't want to talk about. But see, big O is like the most awesome thing ever. So we're always trying to bound our error on the target data. So here's our error on the target data. Here's our average training error. So we train on both the source data and the target data together. Here I've just assumed that we have equal amounts, but if you have unequal amounts, then it's the obvious weighted fraction. So if we have equal amounts, then we have our average training error. We get our complexity term, just like we had in normal supervised learning. So the more complex your model is, the worse you're going to do. And then we have these two remaining terms. So the first one is the one with our familiar 1 over square root number of data points. So basically, this is the number of source points you have and the number of target points you have. So getting more source points helps, getting more target points helps. This is not too surprising. And then the last term is this domain divergence term. So this is sometimes called the H delta H difference or the A distance. But basically what it's doing is it's measuring the distance between these domains in exactly the way we were talking about before. So what we're going to do is we're going to train a classifier to separate source from target, and then we're going to look at the error rate of this classifier. So if the error rate is high, then it means they're hard to separate, which means they're similar. If the error rate is low, then it means they're easy to separate, which means they're very dissimilar. Okay, so we can turn our classification error rate in terms of separating source points from target points into a distance by just doing 1 minus the error. This gives us this H delta H distance, or an approximation to the H delta H distance. And we're basically paying this much penalty. Okay, so why does this provide an explanation for these results? So the thing to keep in mind is that when we're training on, say, just the source data, then this term goes away. Sorry, let me say that again. If we're training just on the target data, then this term goes away, but we have no source points. Right? When we train on both, we pay this H delta H, but we have source points now. And so we're basically playing this balancing act where as we add more and more source data, we're gaining because this numerator is going up, so this whole term is going down. But we're paying because H delta H is going up. And so if you sort of work through the details, this essentially provides an explanation for why the difference between the source-only error rate and the target-only error rate essentially predicts how well this model is going to do. So I actually thought this was really cool because this was just sort of an off-the-cuff observation we made. And then we decided, well, let's prove something about this algorithm. And it turns out that the sort of natural thing that we proved, I mean, you can argue about how natural this is, but it seemed natural at the time, essentially explains the phenomenon that we had observed almost perfectly. Okay, so I think that the big takeaway message here is that whenever you're doing supervised adaptation, you're going to have this trade-off between you get more examples by adding in source points, which is going to help because having more examples always helps, but then you're going to have to pay for it in terms of how far apart the distributions are. And if they're close, then you don't have to pay much. If they're far, then you're going to pay a lot. Okay? All right. All right, so there's another way of looking at this, this sort of augmentation model that's going to move us from this feature-based approach to a parameter-based approach. So you can actually think of what the augmentation is doing, not in terms of adding extra features, but just in terms of learning more complicated models. Okay, so here we have our source points in blue, and here we have our target points in red. And so I can learn a classifier just on the basis of the source points and get maybe this blue line. I can learn a classifier just on the basis of the target points and get this red line. If I think of these as weight vectors, so WS and WT, then the difference between WS and WT, which I've called V, is exactly the shared space. Okay, so V is going to capture what's common between the two domains, and then however WS and WT differ from V are going to capture what's different between the two domains. Okay, so it's kind of an easy observation. You actually have to make this observation in order to prove the thing that I showed before. But what we're going to do is we're going to write our target classifier as the sum of our source classifier and this other vector V. Okay, so if we were just learning the source classifier, then we're going to go through some process where we say, okay, I want a source classifier that gets low error rate on the training data, but is also simple, and simple usually means close to 0. And so what I'm going to do in this setting is I'm going to say, okay, I'm going to simultaneously learn my source classifier and then this V guy, and I'm going to encourage the source classifier to be simple and close to 0, and then I'm going to encourage V to be simple and close to 0. So this is saying I want a simple source classifier. This is saying I want my target classifier to be close to my source classifier. All right, and so it turns out that if you do this, you're basically doing the same thing as the feature augmentation method. All right, are we happy? Okay, I will take no response as signs of happiness. All right. Okay, so we've now sort of gone into this space where we're no longer talking about doing domain adaptation by playing with features into the space where we're doing domain adaptation by playing with parameters. So we're finding alternative parametric representations of our models that we think are going to be good from a domain adaptation perspective. Okay, so it becomes natural at this point, I think, to start thinking about this purely in terms of probabilistic classifiers, but I should mention that all of this stuff can be done in the non-probabilistic world too. Okay, so who's ever seen notation like that? Okay, who hasn't seen notation like that? Okay, so I'll go through it really quickly. So the idea is we're going to have a probabilistic model. We have a bunch of random variables in this model. And we're going to draw them as a picture because pictures are friendlier than math. Okay, so what do we have? So we have our inputs X. So these are, say, our documents. We have our outputs Y. So these are our thumbs up, thumbs down. And then I'm just going to assume for now that we're doing linear classification. So we have some weight vector that makes this classification distinction. Okay, and so basically the nodes in the graph represent the variables in the model, and then the directed edges indicate some sort of dependence. Okay, so the idea here is given my weight vector, or given my classifier, and given a data point X, I can predict a label. Okay, this box around X and Y indicates that I have n many copies of this thing. So I have n many data points. So I have x1, x2 up to xn. I have y1, y2 up to yn. And you basically just copy the edges. Okay? So, and then here, I'm trying to indicate, this is sort of non-standard notation, but I'm trying to indicate that I have a preference for w to be close to 0. Okay? So I want W to be simple or small or have large margin or however you want to talk about it. Okay, happy with the notation? If you're not happy with the notation, like yell loud now because it'll get worse. Okay, no yelling. Okay, so one of the first, at least in sort of the speech and language community models that tried to do domain adaptation is basically this model. So what we're going to do is we're going to take our source data. So now we're going to learn a source classifier based on only my source data. Okay, so I take my source data, I learn some weight vector W sub s that's encouraged to be as close to 0 as possible. Then I fix it. So I say, okay, I've learned WS, write it to disk. Now I'm going to learn some WT that does well on my target data that's encouraged to be as close to WS as possible. Okay, so just like I was encouraging WS to be close to 0, I'm now encouraging WT to be close to WS. Okay? It's pretty simple. And it actually works pretty well. So this is, if we go back to this figure, this model is the prior model. So it doesn't win that often. I mean, it wins in a couple of cases, but it's rarely very far off, right? It's off by like 0.3 error, 0.1 error, 0.02 error, and so on. So it does quite competitively. It doesn't win all the time, but it does well. And actually, you can, if you write it down, you can see that the models are doing almost exactly the same thing. Okay, so this was the first attempt. And basically, people have gotten fancier over the past couple years since this came out. So the first thing you can do is you can say, well, you know, in this model, I first estimated WS, then I wrote it to disk, and then I estimated WT, but why not estimate them both together, right? Like, so in this model, the source data can help the target classifier, but the target data can't help the source classifier. So let's let them help each other. Maybe that'll make things better. Yeah. Yeah. Okay, so here's one attempt. So now what do we have? So we have our source data sitting over here, our target data sitting over here. We have a source classifier WS. We have a target classifier WT. These are both encouraged to be as similar as possible to some W0. I don't know what W0 is. I have to estimate that too. But W0 is encouraged to be close to 0. Okay, so one way of thinking about this is, let's say I have no data. Okay, if I have no data, then W0 should probably just be all zeros. Right? There's no reason to make anything non-zero, so just make W0 all zeros. Now, once I start seeing source data, this is going to encourage me to make WS good for the source data, which is going to make W0 close to WS, because WS and W0 like to be close in this model. Once I start seeing target data, that's going to influence WT. And now WT and W0 are going to want to be close. And so in a sense, W0 is going to be kind of like the general weights that apply to features across both domains, like good, bad, horrible, terrible, etc. And then how WS and WT differ from W0 are going to be the ways in which the domains differ. So exciting, thrilling, boring, whatever. Okay, so we have a more complicated estimation task here, right? So one nice thing about this previous model is you can do it using essentially off-the-shelf classifiers. So you just run a classifier to learn this, and then if you do a little bit of, you know, change like 3 lines of code, you can run your same classifier to learn this. Now life is a little bit more complicated because I have like this thing that I'm trying to estimate, and this thing that I'm trying to estimate, and this thing that I'm trying to estimate, and they're all dependent on each other. So you have to be a little bit more clever about how you do the learning, but you can do it. It's not too bad. And it helps by a little bit. Okay, so now we say, well, this model looks very symmetric, right? It's nice and symmetric between the source domain and the target domain. So I don't even need to have just 2 domains. I can have as many domains as I want. Okay, so now we have essentially the same model, where instead of having 2 domains, we have k domains. For each domain, we have a weight vector for that domain. All of these are encouraged to be similar to W0, and then the weight vector for the kth domain is trained on the data from the kth domain. Okay, so we now have a situation where the model extends nicely from the 2-domain case to the as many domains as you want case. Okay? All right. So what's wrong with this model? Oh, I have one more comment. So now, based on what I've described, I can quickly describe 3 papers that were published and each took about 8 pages to describe. Okay, paper 1 is by Jenny Finkel. So she says, these are all little probabilistic models. So let's say that W0 is a Gaussian variable centered around 0, and WK is a Gaussian variable centered around W0. Okay? This is now Jenny's paper. All right, so then there was another paper, I can't remember who this is by, but they said, no, I don't want them to be Gaussian, I want them to be a Gaussian process. So Mark talked about SVMs, right?
No.
You didn't talk about SVMs. I know you didn't talk about Gaussian processes. Okay, if you know SVMs, Gaussian process is like the probabilistic version of an SVM. So it's basically like going from a Gaussian distribution to a Gaussian process. The main thing you get is nonlinear classifiers. Okay, so now I'm going to say, instead of having everything distributed Gaussian, I'm going to have everything distributed Gaussian process. But other than that, the model stays the same. Okay.
This K is different from the other.
Yeah, so this K is actually the kernel. Oh, sorry, that's totally confusing. Yeah, so this K is the kernel. This K is the number of tasks. Okay, or you could say, well, okay, so one of the big problems in like domain adaptation is maybe I give you 5 domains that are really similar, and then I give you the 6th like wacky domain that just confuses everything. So what I'd like to do is I'd like to share stuff among the domains that are similar and let the wacky domains go off and do their own thing. Okay, so one way of thinking about this is I get, say, 100 domains in, and I'm going to say, okay, these 50 behave similarly, and then these 30 behave similarly, and then these 10 behave similarly, and then the rest are kind of off on their own. Okay, so I'm going to cluster the domains based on how they behave, and then I'm going to learn separate models for each of these clusters. So it turns out you can do this in a sort of purely probabilistic way using this magical thing called a Dirichlet process, which I definitely don't want to talk about, but it's just a way of basically partitioning your data up into different clusters. Okay, so we now say, essentially the way to read this is cluster your domains into ones that behave similarly. For each domain, learn a shared parameter, and don't tie the parameters across the different domains. Okay, and so this was another paper. This paper was actually like 30 pages long. But if you understand the picture, these 3 are basically the same. They just change the distributions a little bit. Ironically, actually, this one came first, and this one came second, and that top one came third, which is sort of the preference in academia for doing the more complicated thing first rather than doing the less complicated thing. Okay, so one of the problems with this tree model is that not all domains are created equal. So here's domains from Mark's Amazon data. So we have appliances, kitchen, electronics, other, music, books, DVD, and video. And if we just take the reviews in these different domains and we do some sort of hierarchical clustering, what we see is that appliances and kitchen seem very similar, electronics and others seem very similar, DVD and video seem very similar. That's totally plausible. Books is kind of like DVD and video, but not much. Music is kind of like these things, but not much. And then these 2 sides are very unlike each other. Okay, so the idea is that, if you believe this tree, then what it's kind of telling you is that you should share a lot of stuff between appliances and kitchen, and you should share a lot of stuff between DVD and video, but maybe you shouldn't share so much stuff between video and electronics. Okay, and these previous models basically treat each domain as if it were completely equal. Okay, so what we'd like is we'd like a model that can use knowledge like this. Okay, so the big question is, how do we do this? One thing you could do is you could cluster the data like this and then try to craft a model based on that clustering. The problem with doing this is that maybe this clustering is good for explaining what the documents look like, but it might not be good for explaining the classification decisions. And what we'd really like is we'd like a tree that says, from a classification perspective, DVDs and videos classify very similarly, and appliances and kitchen classify very similarly. Whether the actual text in appliances and kitchen is similar or not, we don't really care. We only care about the classification decision. So what we want to do is we want to learn a tree that's good for making classification decisions at the same time that we learn how to classify. Okay, so, yeah.
Isn't that what your current model is doing? The current model? Like, what's the difference between that?
Oh, this one? Yeah. Okay, so let me actually answer that at the end, because there's actually a very good answer to that, but I won't be able to explain it yet. I mean, I guess at a high level, this is sort of all or nothing. Like either you're in the same cluster or you're not in the same cluster, whereas the tree allows for sort of gradations of sameness. But there's a better answer than that, but I'll have to say at the end. Okay, so in order to do this, we need a little bit of technology. So I'm going to go through the technology really quickly because it's not like super important from a domain adaptation perspective, but I think it's really fun and cool, so you have to see a little bit of it. Okay, so we're going to do this in a probabilistic setting, which means we need a probability distribution over trees. And it turns out that people in genetics care a lot about probability distributions over trees because people in genetics basically study trees. That's like what they do for a living. One particularly elegant model is this thing called Kingman's coalescent. So it's a model for the genealogy of a haploid population. So a haploid organism is one that has exactly one parent. So we're not haploid. Let me just show how it works. Okay, so we have n individuals currently, and we're going to work backwards in time. Okay, so at every generation, we're also going to have n individuals. So at time -1, we have n individuals. At time -2, we have n individuals backward through time. And then to go from our generation at time t to a generation at time t -1, every individual at the current time is going to uniformly select an individual from the previous time as their parent. So some of these guys aren't going to get selected at all. Some of them are going to get selected multiple times. Some of them will get selected once, and so on. Okay, then these guys all select parents. These guys all select parents, and it goes back. Okay, so you can prove that in the limit, this will form a tree. It's not that hard. Kind of has to eventually. I mean, the main thing to show is that it actually happens, right? I mean, how do you know these things don't just migrate off into infinity? But it does happen. So in the limit, these things form a tree. So we can take some ancestor and look down, and we get a tree. So what we're going to do now is we're going to take limits on both sides of this. So we're going to take the limit as time goes back to infinity, and the limit as the number of individuals goes to infinity. And the reason we do this is because we essentially need this to make the whole thing a tree going back to the beginning of time. Okay, so if we can do this, then if I sort of have removed the intermediate ancestors that don't mean anything, we end up with some tree structure that looks like this. So these two individuals, let's see if we can see it, right? So these two individuals have a common ancestor back here. So I've just removed all of the intermediate ancestors because it's basically like this guy has a parent, has a parent, has a parent, has a parent, and eventually gets here. Okay, so we now have this tree structure. It's actually almost guaranteed to be binary branching. And we're now going to take the backward edges and flip them around into a model like the ones we've been seeing before. So before we had, 0 going to weight, going to weight, going to y. So now we're going to have some weight vector here generating a weight vector here and here, which generates weight vectors at the bottom. Okay, so the way to think about it is the individuals are going to be the different domains. The ancestry is going to be how these domains relate to each other. So in this case, these top two domains are going to be very similar. The top domain and the bottom domain are going to be very different. And then these intermediate nodes are sort of these hallucinated weight vectors that are good at explaining these two domains, but not the other domains. Okay, so this thing seems complicated. I mean, we have infinitely many individuals going back infinitely far in time. Can you actually compute? The answer is yes. So you can actually construct these trees greedily in a bottom-up manner. It's very similar to sort of standard agglomerative clustering if you've seen it. And the magic is really how do you deal with these intermediate nodes. And it turns out that since this thing is tree structured, you can run essentially a dynamic programming algorithm called belief propagation that will fill in the values of the intermediate nodes. Okay, so what do we do now? So we now have a model where instead of having a flat structure where we say there's a W0 and then there's W for domain 1, W for domain 2, W for domain 3, W for domain 4, and they're all connected flatly, we now have this sort of true hierarchical structure. Okay, so we now have to do inference in this model, so we're going to do EM, which you guys are going to play with this afternoon, although not for this model. And there are two steps. So the first step is basically given the tree structure, find all of the weights in the interior nodes of the tree. And then the second step is given the weights at the nodes in the tree, recompute the tree structure. Okay, so the E step, so computing expectations over the weights, can be done by this belief propagation process. And then maximizing the tree structure can be done by this agglomerative clustering algorithm that we have. Okay, so one thing that comes out of this is the figure that I showed before is the figure that you get if you just cluster based on the documents rather than clustering based on the classification rules. This is the tree that you get at the end of the EM process, which is essentially based only on the classification rules. So one of the things that, I don't know, makes a lot of sense to me is that over here, books is pretty far from DVDs and videos, and music is like super far from DVDs and videos. Even though, I don't know, from like a sentiment perspective, what I'm going to use to describe books and videos and DVDs are probably all going to be about the same, right? Like they're all a storytelling process. So what I think is good in a book is probably also what I'm going to think is good in a DVD or a video. And what we see is that when you do the clustering based on the classification decision, this is what you get. So DVDs are very similar to music, which is very similar to books, which is very similar to video. Electronics and other are sort of sitting over here by themselves, and then appliances and kitchen are similar, but the fact that these are connected way up here rather than way down here basically says they're not that similar. They're kind of similar, but not super similar. And without going through like all the details, basically if you do this, it works really well. So the red line is this model, higher is better. And the most interesting thing is that which one is it? The green line is essentially what you get if you use this tree as a fixed tree. And the red line is what you get if you infer the tree as part of the classification process. So basically what this is saying is that just inferring a tree and crossing your fingers and hoping that it does a good job isn't going to work nearly as well as if you infer it as part of the classification process. Do you have a question?
For the previous slide, is there some distance? Because you said that DVDs and music are very similar, and like there's a big step then when.
So what does the distance mean? Okay, so the distance means, so there are two ways of answering this. So in the coalescent model, the distance is basically how many generations until we have a common ancestor. in the domain adaptation setting, the way that it works is that we basically have, say, a shared weight vector here, which gives rise to a weight vector here and a weight vector here. The longer the branches are, the more I'm allowed to vary from this guy. Okay, so in this case, since this branch is very short, the weight vector for DVDs and the weight vector for music both have to be very similar to the weight vector here. But since this is high, I'm going to have something here and something at these two places, but they can vary quite a bit. I mean, it's how I parameterize the model, but the distance is basically how far away are you allowed to move. Does that make sense?
Skip some generations, or in the...
Say that again?
If I do, for example, word clustering, so in every generation I must merge two classes together, but here I think you skip some, like the bigger distance.
Yeah, so this is a detail that I elided over. So it turns out that when you take this model and you take the infinite limit, and I ask myself, what's the probability? Okay, so given two nodes, what's the probability that they've merged within k units of time? It turns out that this is an exponential distribution parameterized by k, which is actually super important because exponential is memoryless, and it means that this thing is well behaved and stuff like that. But that's where it comes from. So it's because they're always choosing uniformly from the previous ancestry, gives rise to this exponential fall off in the length of the ancestry path. Okay. That's also important for inference because it means that you don't have to say, okay, leave it alone for a generation. You can just say, I'm going to merge these two, and then the only question is, how far back did I merge them? Okay, so that's basically all I want to say. So I think that the main messages are kind of, if you have no labeled data in your target domain, then you should at least try doing this instance weighting thing because it's super, super easy, and it can help a lot. Okay, so that's message number one. Message number two is if you do have labeled data, you should at the very least try this augment approach because it takes it's like one line in MATLAB or like 5 lines in Perl, or I mean, it's like it takes absolutely no effort and it almost always helps. And it's not me who's saying it all. I mean, it is me who's saying it almost always helps, but other people have sent me emails and they're like, gee, I tried this and it actually works. And I'm like, yeah, I know it actually works. I think that the big sort of, I don't know, I mean, so this style of model has been very fruitful for a while, but one of the things that I think is, sort of getting more and more interesting as time goes on is to move from the setting where we have 2 domains or 3 domains or 10 domains to a setting where we have like thousands or millions of domains. So one of the things that I want is, I have my phone, I walk around, I take pictures of stuff, and if I take a picture of the Eiffel Tower, it should automatically label it as the Eiffel Tower, right? It just should, right? Why can't it do that? And then, if I'm walking around like campus and I take a picture of a building, I'd like it to be able to label it as the building. But if I'm walking around my house and I take a picture of my cat, I don't know. Maybe it could say cat, but whether it actually identifies my cat's name or not is sort of a question. And so, one of the things that I think is interesting to think about is, if we take this model where, every person has some smartphone and they're going around and doing stuff, there's things that we want to be shared, right? So, if 10 people have gone to the Eiffel Tower and taken pictures, this information should be shared. But, if I go, I can't think of a great, I don't know, if I'm going around taking pictures of my cat, I don't know that this information should be shared. You can think of examples other than just a cat that probably shouldn't be shared as well. But I don't know. I think that this is an interesting approach. The problem is that, the sorts of algorithms that we've been talking about and the sorts of theory that we have really don't scale to the case where we have a huge number of domains. So I don't know. That's one direction that I think is really interesting. I think that this general approach we've kind of milked for about all we're going to get out of it. And I think that if we're going to sort of move further, we need sort of fresh new ideas. Anyway, there's plenty of work that's yet to be done, and you guys should do it. So I can stop. All right, thanks.